one of the most fundamental results in linear algebra. So, first of all, the adjoint. Only defined in terms of inner products, you move the operator to the other side, and then that's the adjoint. The matrix representation in a finite dimensional space is the complex conjugate transpose of the original matrix. Let's just do an example in reals to see. So I've got some matrix taking R3 to R2. When I won't say matrix, I'll just do linear transformation. So I've got a 3 vector that's being mapped to a 2 vector. I look at the inner product, the definition of the adjoint, move it over to the other side, and compute. For inner product, I'll just use the standard real inner product of transpose. Multiply out. So the transpose operator takes R2 to R3. So that's an R3 vector. So I'm going to need it X transpose applied to some R3 vector. X1 terms, X2 terms, X3 terms. This is the action of the transpose on Y, where Y is an element in R2. So to get the matrix representations, I need to break it down in terms of the basis vectors. X1, X2, and X3 are scaling the standard basis elements, so where they go to are the columns of the matrix. And the same is true for the adjoint. I break it down into Y1 and Y2, which are scaling the first and second basis vectors, so those become the first and second column of my matrix. That is, the complex conjugate is the same example with complex numbers. Here becomes one of the fundamental theorems of applied math, is how the domain and range then fit together with the adjoint. So the domain and the range are going to break into two orthogonal pieces. So the range of T and the null space of the adjoint, and then the null space of T and the range of the adjoint. These are orthogonal to each other. The proof will be an exercise, but it's not hard. You just write down the definition of adjoint and it's almost immediate. And once you get one of these relationships, all the others come pretty quickly. Spectral theorem, here we go. This is what we've been leading up to the whole course. I can find a diagonal matrix for T with the eigenvalues on the diagonal. The change of basis I'm going to do is the eigenvectors as columns for my basis elements. And I can make the inverse the conjugate transpose. That's the spectral theorem. for real matrices, I need T to be self-adjoint. For complex matrices, I need T to be normal. Normal is almost like self-adjoint, but just slightly weaker. It means that the conjugate and T commute with each other. We won't do the real proof. Turns out it's harder. Fundamental theorem problems. So we're going to prove the complex case. So normal conjugate commutes with the matrix. We assume that. And now we'll use our previous knowledge. With a complex matrix, we know we have one eigenvalue eigenvector, so I'll do Gram-Schmidt. And then I'll get a QR decomposition using that one eigenvector as a seed. That gives me an upper triangular matrix with respect to some orthonormal basis, where the first vector is an eigenvector. This is called Schur's theorem. So from the video, we'll just do the 3 case, because once you can do 3, you can do n. It's the same pattern. We just need to get the pattern going. And 3 is usually sufficient to see the pattern develop. So there's our R matrix. We'll use the lemma we proved in class. That the length of T and the length of the adjoint on the same vector is the same. Well, that immediately implies, since all the components are positive, that R1, 2, and R3 must be 0. So I'll update my matrix. And now we'll repeat the exact same thing for E2. With my new updated entries, I'm back to the same thing we just got done doing, with just less terms. By the same reasoning, I'm adding a positive number. That must be then 0. Update my matrix, and it's diagonal. So there's our R matrix. Our Q matrix is just an orthonormal basis. I don't know that they're all eigenvectors yet. So when we get our QR decomposition, we use the identity matrix in the domain. For the spectral theorem, we're going to use the Q matrix for both domain and range, because we're having a space mapped to itself, so I can use the same change of basis. We still have to show that the inverse is the conjugate transpose for this Q, but we'll do that after this. We'll run it through the change of basis, and lo and behold, eigenvector eigenvalue pairs. It's just as true for every index as it is true for the first. Eigenvalues on the diagonal, Q is eigenvectors. The last thing to finish is that the inverse is the conjugate transpose. We'll use a result we did way before the coronavirus, was that if ST has identity, when you commute them, it has to also be identity. So conjugate transpose, these are all row vectors, Q, column vectors, and now I can compute their product. Row column entries are the row column entries for the product matrix. And I just write them all down. Because the F's are orthonormal, every one of these entries is 0 except for the diagonal. So Q conjugate transpose Q is the identity. By the result we proved a month ago, that also means that Q Q conjugate transpose is also identity. There's only one matrix that does that. That's the identity matrix.